We have looked at the model of the PMOS transistor and have seen that it's exactly the same as that of the NMOS transistor, but with currents and voltages reversed in polarity. Now we will look at the small signal picture of the PMOS transistor. Okay. So just to recap, the large signal characteristic of the PMOS transistor is described in terms of VSG and VSD, and the drain current ID is written as a function of these two voltages. Okay, I'll write down only the saturation region equation here. Mu P Cox by 2 W by L VSG minus VTP square. This is the model we considered. And just like with NMOS transistor, there can be channel length modulation or dependence of the drain current on VSD in the saturation region, and that is denoted by an additional factor 1 plus lambda VSD. Okay. I won't draw the graph corresponding to this, but it will be the same as that in the NMOS transistor. Okay. This of course is only in saturation region. Now, what about the incremental model of the MOS transistor for small increments or the small signal model? If we have an increment of lowercase VSG in this source gate voltage and a lowercase VSD in the source drain voltage, there will be a certain current increment ID in the drain current. Okay. The incremental model or the small signal model describes the relationship between these incremental quantities lowercase id, VSG and VSD. Okay. Now we know that for a general nonlinearity, if some current, let's say I2, is a function of two voltages V1 and V2, then I2 plus increment in I2 will of course be the same function of V1 plus an increment in V1 and V2 plus the increment in V2. Okay. Now what was the relationship between the incremental quantities? We saw that I2 would be the partial derivative of uppercase I2 with respect to V1 at the operating point times the increment in V1 plus the partial derivative with respect to V2 at the operating point times the increment in V2, and exactly the same thing holds here as well. Okay, so let's see what that gives us. We have the operating point quantities VSG and VSD and ID, let's say, and we have the incremental quantities lowercase VSG, lowercase VSD and lowercase ID. Okay. Now we want to form an equivalent circuit which deals with the increments alone. This is the source, this is the gate, this is the drain, and similarly I'll draw the source, gate and drain here. And because Ig is 0, the gate current is 0 in a PMOS transistor as well, this gate terminal will be an open circuit in the incremental picture. Okay. Now this incremental current lowercase id flows from source to drain. Okay. This is the incremental current that is shown in this picture. What is that equal to? It is the partial derivative of ID with respect to VSG at the operating point times the increment VSG plus the partial derivative of ID with respect to VSD again at the operating point times the increment VSD. Okay. So we have VSG over here and VSD over there. Okay. Now let's consider these quantities one by one. We have the partial derivative with respect to VSG. ID, again I will do this only in saturation region, but like NMOS you can also evaluate it in the triode region and so on. Mu P Cox by 2 W by L VSG minus VTP square 1 plus lambda VSD. Partial derivative with respect to VSG is mu P Cox W by L VSG minus VTP times 1 plus lambda VSD. Okay. Now this is the usual expression for GM, and many times we even approximate it by just this part because lambda is small. This is the same thing that we did for the NMOS case. Okay. Usually for most operating point calculations we just ignore lambda. Okay. Okay, and this is nothing but the GM of the MOS transistor, and you can see that the expression is the same as before, except instead of VGS we have VSG. That's because all polarities in the PMOS transistor are reversed. Okay, and if you have both NMOS and PMOS transistors, you could distinguish this by saying GMP or using some other extra subscript. Okay, so we have GM, and this simply says that ID will be GM times VSG, and of course the GM is calculated at the operating point. That is, the value of VSG that you use here and VSD that you use there will be at the operating point. Okay, plus this part here, and that again, let me copy this over there. Partial derivative with respect to VSD will be mu P Cox by 2 W by L VSG minus VTP square times lambda. Okay, and this approximately equals the operating point current, so this is approximately lambda times ID, and this is the expression that is used most often to calculate this. I know what this is. This is the output conductance GDS of the MOS transistor. Okay. So the expression comes out very similar to what we had in case of except that instead of VGS and VDS we have VSG and VSD. Okay. ID flows from source to drain, and it depends on this VSG. So this term here is represented by a current source, which is GM calculated at the operating point times VSG. And to represent this term, we recognize that ID flows from source to drain, and it is also dependent on the voltage between source and drain. Okay, so it is a conductance. This is the GDS calculated at the operating point. It's a conductance whose value is GDS. Okay, so it looks like the incremental picture of the PMOS transistor is similar to that of NMOS transistor, but with the polarities reversed. Okay, but we will make some change to this. That is the following. Let me copy this over. Now in case of the NMOS transistor, the model was in terms of VGS and VDS, and the picture looked like this. This is the source, this is the gate, this is the drain, this is GDS, this is GM times VGS. Okay, whereas this is the model for the PMOS transistor. It is written in terms of VSG and VSD, and the incremental current source points from source to drain instead of from drain to source. Okay. Now let's say that we represent this also in terms of VGS and VDS. That we can do, right? Because VSG is minus VGS and VSD is minus VDS. If I do that, what do I get? Let me still write the source here, gate there and the drain there. Now I'll use VGS as the variable instead of VSG. All I have to do is recognize that this current source is GM times VSG. Okay. This current source here is GM times VSG, which of course is minus GM times VGS, because VGS is simply minus VSG. Okay. And I'll also use VDS. As far as the conductance is concerned, the picture remains exactly the same. There is a conductance between drain and source. Okay. Obviously, this doesn't depend on whether you choose VSD or VDS. Okay. Because if you choose VSD, then you will say that VSD times GDS will be flowing in that direction. Alternatively, if you choose VDS as the variable, which would be in the opposite polarity, VDS times GDS would be flowing in that direction, which is exactly the same. Okay. You can see that VSD times GDS flowing downwards is exactly the same as VDS times GDS flowing upwards. Okay. So there is no change there. Now this current source here is flowing from source to drain and it has a value minus GM VGS, and I can get rid of the minus sign by reversing the direction of the current source. I can make it flow from drain to source, in which case its value will simply be GM at the operating point times VGS. Okay. Now why did I do all this? If you do this, you will see that the incremental picture of the PMOS transistor and the NMOS transistor are exactly the same. It's now drawn in a weird way, but you see that you have gate source voltage defined from gate to source, the same as here. You have this incremental current source going from drain to source, the same as here, and its value of course is GM times VGS, the same as here, and you have a conductance between drain and source. So incrementally, when you express everything in terms of VGS and VDS, the pictures of the NMOS and PMOS transistors are exactly the same. Okay. So we will draw the picture this way for the PMOS transistor as well. All I did was I started off with VSG and VSD, which was the variables we originally used to describe the PMOS transistor, and I changed them to VGS and VDS. Okay. With that change, you see that the incremental picture of the PMOS and NMOS are exactly the same. Now this is actually a big advantage, because when we try to synthesize the function of any circuit, we do it in the small signal domain. That is, when we realize the control sources and so on, right? We did it in the incremental domain or the small signal domain first, and then we added the operating point arrangement to it. Okay. Now if the small signal picture of the PMOS and NMOS are exactly the same, whatever picture we use for NMOS can be used for PMOS. Okay. So whatever we derived as the incremental picture for all the 4 control sources or even the common source amplifier can be used as it is, because we will still describe the incremental picture of the PMOS like this, right, in terms of VGS and VDS. Whereas only for the large signal or the operating point picture, we will use VSD and VSG. Okay. So that is one thing. Whatever work we did with NMOS transistor can be used with PMOS transistor. Also, when you have a circuit with multiple transistors, you can first synthesize the circuit functionality in the small signal domain without worrying about whether you are going to use NMOS transistor or PMOS transistor in a given place. Okay. So you have many transistors or even a single transistor. You can first synthesize the function and later decide which one to use, PMOS or NMOS. That may be based on some other criterion, some measure of convenience or performance. Okay, so all the synthesis of functionality is done in the incremental domain with a model of the MOS transistor which uses VGS and VDS. This is so that you can later decide whether to use NMOS or PMOS, and this model is equally applicable to both. Okay. So the bottom line is that the incremental small signal models of PMOS and NMOS are the same, and it's this, and it's usually also drawn like this. Okay, at least whenever possible, with VGS, GM-VGS and a conductance GDS between drain and source. And in case you are still wondering how NMOS and PMOS came out to have the same incremental model, we can also go back to the large signal picture. This is for NMOS, and we describe it in terms of VGS and VDS. The current flows from drain to source. And in PMOS, on the other hand, the current which is defined as flowing from source to drain is described in terms of VSG and VSD. Okay. Now let me just illustrate this by considering an increment in this voltage VGS. Okay. So let's say I have a positive increment in VGS. So this means that ID increases. So there is a positive increment delta ID, that is a positive increment delta ID flowing from drain to source. Okay. Now here I have the voltage as VSG, and I'll consider a positive increment of delta in VGS. Okay. So this obviously means a negative increment of delta in VSG. Okay. So we have VSG minus delta. If the value of VSG reduces, the current flowing from source to drain reduces. Okay. And you can equally well think of it as an increment in this direction, delta ID from drain to source. And you can see it's exactly the same. So a positive increment delta in VGS will cause an increment delta ID from drain to source where delta ID is positive. Similarly, a positive increment of delta in VGS, which is the same as negative increment of delta in VSG, will cause the drain current to reduce, but this drain current is flowing from source to drain. So you can think of it as a positive increment from drain to source. So the incremental pictures are exactly the same for PMOS and NMOS. Okay.